All right, so as discussed, we want to just go over a little bit about errors and uncertainty when taking scientific measurements before you guys actually start taking data, so you can have an idea of what sort of things you want to be looking for as you go through and do your calibration. So when we talk about error in a scientific measurement, we are making a specific kind of statement. We are basically stating what our best guess is of the true value of a quantity, and then how close we think other possible values are to that. So you're making some kind of numerical statement, along the lines of, if I say the height of a tree is 11 feet plus or minus 1 foot, what I really mean is I think there's a 95% chance that the true height of the tree is somewhere between 10 and 12 feet, and my best guess is that it's 11 feet. And it's important to understand that every actual measured quantity has some level of uncertainty to it. You don't have any kind of perfect ruler or measurement device. So anytime you make a measurement, there's always some sort of variability or uncertainty or unknown to it. But when we say error, we don't mean, hey, we made an incorrect measurement or this is just human error. So if we thought there was something wrong with a measurement and we had evidence, that there was something wrong, you would probably not want to use that measurement. So in general, there are two types of error. You have random and systematic errors. Random errors are random fluctuations either around an average or around a true value. And usually you make the assumption that there's some sort of underlying statistical distribution there. And because of that, you can make, some sort of calculation about that. Most importantly, it's the sort of error that you expect if you were to make multiple repeated measurements, that error would average out, and if you took the average, it would be a good representation of your measurement. So the sort of things this can be is, electrical noise, maybe the variability in reading out a mechanical gauge. If some people slightly have their heads to the right or the left, they're going to read slightly different numbers. And because you don't expect any sort of everyone always to the right and always reads it high, or everyone always to the left and reads it low, you expect whatever that error is to be random. Also, you may have actual physical processes. For example, in radioactive decay, if you're counting decays, the underlying thing is based on a random process. So when you measure it, you're going to get a random value. And the other type of error is systematic error. And I know this seems pedantic, but the most important thing about it is it's not a random error. It may be the sort of thing where you're always tending to read a higher value. But the important thing is, because it's not random, it's not the sort of thing where you can just make repeated measurements and average over them to get rid of it. There's no sort of systematic mathematical representation. You can't do detailed calculations on it because of that. It may just be that your ruler is slightly too short, so it always reads a little bit off. So the sort of things that you want to consider as systematic is, maybe there was an error in the calibration. Maybe there's a limit in the resolution. If you're using a digital device, you wouldn't, the smallest accuracy you could say is whatever that lowest digit is. you wouldn't be able to tell, if something was between a half or a quarter of the smallest number that you can read on that display. So you want to be able to assess how big that random error is. So you can look at this random error over, if you take multiple measurements, you can get an idea of how much they're spread. And what you can do is make a calculation of the standard deviation, which is the equation shown here on the right. Most importantly, this is the sample standard deviation as opposed to the population standard deviation. You may see two different things called the standard deviation, and you should be aware of this is the version you want. Next Thursday, we're actually going to go into a little bit more detail about the difference between them. But for now, you just want to know that this is the one you want to use. And, you can sort of tell that it's the right one. So if I was to take a single measurement, I wouldn't be able to tell anything about how spread out that would be over multiple measurements, right? So if I have n equals 1, the standard deviation blows up because I can't really say anything meaningful about what that spread is in that measurement. Additionally, you want to know how good a representation your average is, your mean is. And for that, you use something called the standard deviation of the mean. And that's just, you take the sample standard deviation squared and you divide by the number of measurements you take. So as you take more and more measurements, the standard deviation of the mean gets smaller, your mean becomes a more accurate measurement, which is sort of what you would expect with a random error. And just as a sort of, if you're taking measurements and you want a quick guess of, how big of that is, you can just look at how spread is your highest and lowest value. And you can tell that that'll actually be larger than your sample standard deviation. But usually while you're conducting an experiment, you want to be able to see just as a sense of a rough estimate of how big that is. So the other important type of error, like I said, is systematic error. So there's not a formula for telling how big your systematic is. You sort of have to think about how you're making this measurement, what you're using to measure, and make a assessment of how accurate that is. So if you had, a very accurate other device that you could compare what you're using to, you could do that. Also, you could do a calibration, or you could measure something that is of a fixed standardized amount. For example, if you're using a scale to verify that it's working right, whether it's like a 3-beam balance or a digital scale, one of the things you can do is put a standard, for example, 100-gram weight on it and verify that you in fact do get 100 grams when you weigh that. Also, most manufacturers will give you some sort of specification in the manual, especially for electronic measurement devices such as multimeters and oscilloscopes. And they will give you a value for the accuracy. So it'll be something like 1% of full scale, or maybe 5% of the measured value, or 2 digits. Whereas, in the last case, that means, 2 times whatever the last digit on the display is. And finally, if you don't have anything else to go on, you want to assume that the systematic is at least as large as whatever the smallest value or smallest increment you can read with that. So if it's a digital display, you know, whatever the smallest digit is. If it's some sort of mechanical device like a ruler or a gauge, you sort of have to make a judgment call, and often you'll do like half of whatever the marked increment is. But that also depends on how big those increments are. So it's a lot easier to tell the difference between like a quarter of an inch and a half of an inch, as opposed to, you know, a quarter of a millimeter and a half of a millimeter. But sort of the general rule of thumb is use half an increment if you think that you can see in between the marked, halfway between the marked values. So for example, you can put a bunch of ammeters in series and then measure the current going through them. So because they're in series, we know that they have to have the same current going through each one of them. And we can measure that all at the same time. So for example, and this was actually done here on LSU, we put, what is that, 7 multimeters in series and put about 50 milliamps through them and see what they all read. And you can see that there is some spread between those. So we got his values as low as 49.7 and as high as 50.2. And if you're wondering about the negative in the middle there, that just means that the probes for the multimeter were flipped. So current was flowing in the black terminal and coming out of the red terminal. So if you switch those leads around, that would just become positive. So what could be the source of the difference? Well, there's there's obviously some slight differences in the manufacturing. There's probably, for example, a reference voltage inside the multimeter that's being used to calculate that value, and it may be a little bit off in the different ones. But most importantly, if you were to look up the manual for that multimeter, you would see that what the accuracy the manufacturer gives was 1% of full scale. And that's actually a typo. The full scale on that particular setting was 200 milliamps. So 1% of that would be 2 milliamps. So the scatter that we saw was about 0.2 milliamps. So in fact, all of the multimeters agreed with each other within their specified value. But if we repeat the measurement, each one of those multimeters basically gives the same value within 0.1 milliamps. So the difference between all of those is not random. It's a systematic. If you repeat the measurement with, for example, the one that reads 50.2, you'll get 50.2, 50.2, 50. It wouldn't scatter down to like 49.7. And this is important because that tells you it's a systematic error, and also that in this case, that systematic is large compared to the random error. You don't really see fluctuations, you just get the same value over and over again. So besides your actual measurement device, your experiment itself, depending on how you set it up, could give you a systematic error. So for example, if you're measuring the temperature of a water bath, where did you put the thermometer or the temperature probe? If the water bath is actually sitting on a hot plate and it's actively heating and you haven't stirred the water up, it's going to be closer, or it's going to be hotter at the bottom. Additionally, if the thermometer is actually touching the glass is going to be, which is in contact with the heating element, is actually going to be hotter, most likely, than the water inside the glass. You know, also the value may not be steady. It could be changing. So if you're actively heating up or cooling down the water, the value will change depending on when you read off the temperature. And the important thing with that is to consider, is the value changing fast enough that that's larger than your error? So, you know, if I'm heating up on the order of a degree an hour, it's probably not important, especially if I'm measuring it with a thermometer that's possibly only accurate to half a degree, right? But if it's heating up in, you know, 10 degrees in 3 seconds, well, depending on when I looked at the thermometer, when I made that measurement, I'm going to get a different value. So in general, you want to try and set up your experiment to minimize those types of errors, because they're the types of errors you cannot reduce by taking more and more measurements. They sort of put a lower limit on how or a upper limit on how accurate your measurement can be. So, for example, you want to use the smallest possible scale or the highest possible resolution to measure your value. So if I'm trying to measure the value of a 1.5 volt battery, I'll probably get a more accurate value using the 2 volt scale rather than the 20 volt scale, which is because the accuracy of a multimeter is usually some function of the full scale value. Also, you could let the value that you're trying to measurize stabilize if you're using something that's relatively slow. So, for example, if I'm trying to measure a temperature, it's often easier to measure the temperature of a water bath, because water has a high specific heat, so it takes a lot of energy to heat and cool it, so its temperature doesn't change that quickly unless you're putting a lot of energy into it. As opposed to if I was trying to measure the temperature of some air, that is a lot easier to heat up and cool. So whatever those changes are due to heating and cooling, they're going to be faster and larger. Additionally, you know, if I have a lot of water that I'm trying to use to measure the temperature, well, that's going to heat up and cool down more slowly compared to a small amount of water. You know, it takes 100 milliliters of water will heat and cool more slowly than 10 milliliters. Additionally, you know, you want to try and design your experiment in such a way that you can make these measurements in a consistent and unbiased way. You want, for example, you can always want to make sure your thermometer is always sitting in the same location when you make a measurement. Or another good example is if you look at some high precision pressure gauges, what they'll have is a mirror behind the needle. And what that allows you to do is basically line up the needle with its reflection, and that way you can be sure that you're looking at the needle directly on. Your head isn't slightly to the left or the right and causing you to read a lower or higher value. Another important thing is to ensure that each one of the measurements that you're trying to use together are independent. So what we mean when we say an independent measurement, you mean that measurement does not affect or is not affected by any of the other measurements you're comparing it to. So that is what allows us to average several measurements together and reduce the random error of that average value, because the random values in each of those measurements have nothing to do with each other. If one of those measurements did depend on the other one, well, now the random error of the two measurements is related and it isn't necessarily going to average out. So for example, if I'm trying to measure the wavelength by looking at the distance from peak to peak, like on the graph there, well, I can measure from point A to point B, and that gives me one measurement of the wavelength. So now if I try and get a second measurement of the wavelength by measuring from point B to C, well, that's not independent of the original measurement, because A to B and B to C both depend on wherever that B is. However, I could measure from A to B and then measure from C to D. Those two things, in this case, are not related to each other, so that gives me two independent measures of the wavelength. So usually we don't want to just collect data and have a mess of numbers and be like, yep, this is my data. You want to compare it to some kind of model, which is usually a mathematical representation. It's a line, it's an exponential curve. You're trying to do something that lets you predict future measurements often. So you want to make sure that you have collected enough data points that you can actually tell, well, is the model that I picked, is the equation of this line a good representation of the data? And one thing that's important to note here is if I take repeated measurements, average them together, and use that to do the fit, each one of those averaged values is going to be considered a single point. So one thing that's important to know is if I have an equation that has, constants in it, depending on how many constants and how many points, I can always make a perfect fit. So if I have two constants and like a line which has a slope and a y-intercept, I can always find a line that will connect 2 points. Similarly, if I have a quadratic equation, I can always pick those constants for the quadratic so that it'll go through 3 points, because there's 3 constants in a quadratic equation. So because of this, you always want to have many more data points than the number of constants in your equation. Also, you want to make sure that your points are over a wide enough value to be able to tell if your fit is an accurate representation or not. If I take any arbitrary function, I can zoom in on it, and over a small enough interval, it will look like a straight line. So you want to make sure the points are spread out far enough that you can actually see, okay, wait, this doesn't actually match a straight line. It starts to curve down at the end, or it starts to rise up. Additionally, if your points are too close together, as in the difference between the points is on the same size as the error that you've estimated, well, now you aren't really fitting different data. You're just fitting whatever that random scatter in the data is. So the fit that you get is completely meaningless. So the question is, how many data points do you want to take? So in general, more data is better, but there's a point where you hit a diminishing returns. So for one thing, it takes more time to collect more data, and it takes more time to analyze a larger amount of data. Additionally, you want to consider, are you hitting whatever that limit is of your systematics? So since doing a repeated measurement only reduces the random error, once that standard deviation of the mean is smaller than your systematic error, well, you're just going to get the same value over and over again. You're not going to get an improved accuracy. You know, for example, I can't measure the length of a metal bar down to the nanometer by doing 1,000 measurements with a ruler marked off in millimeters. You know, at some point I hit that limit of, you know, 1 millimeter or half a millimeter. And once I hit that limit, doing more additional measurements doesn't really tell me anything more about the quantity you're trying to study. Additionally, you want to think about, you know, what is the range of values you want your fit to be valid for. In general, interpolating between data points is more accurate than extrapolating, which is when you know, try to extend your model past either below the range or above the range of the actual values you measured. Part of that is because, well, maybe the sensor that you're using the thing you're using to make the measurements, behavior has changed. You know, some things are linear over a small range, but then the behavior changes. Also, whatever uncertainty you have in that fit, it gets larger and larger as you get further and further from the values that you measured. So because of this, you want to basically have at least have a plan before you start taking data. Obviously, you want to try and set up your experiment in a way that minimizes those systematics. For example, you may, if you're measuring the temperature of a water bath, you stir it up before you take your measurement, because hopefully you're trying to equalize the temperature everywhere inside of the beaker. Then you can often, you often want to take an initial set of repeated measurements and then either do a rough estimate of the standard deviation, or just look at how much they're spread, or actually calculate the standard deviation. And that will give you an idea of what is the size of the random error. And then you can compare that to what you have assessed as your systematic error, and you can get an idea of how many repeated measurements do you need to make for each of the points you're going to try and average together, or each of the measurements you're going to average together. Also, going in, you want to have an idea of what type of fit, as in what sort of behavior you expect to see when you make your measurements. Is it going to be a linear relationship? Is it going to be quadratic? Is it going to be exponential? You know, if you expect a exponential rise and you've taken a number of data points and it looks linear, you may want to evaluate, well, do I need to expand the range over the data, the range of the data that you're recording? And you want to space that data out to cover the full range that you want to try and cover, as well as spacing the measurements out enough that you're not doing the thing where you're just plotting or you're fitting the noise. And so one thing you can do is look at the data sheet for whatever you're using to make this measurement, or whatever theory is behind the sensor, or the theory behind the actual physical process you're trying to study, and you can look at, this is the sort of behavior I expect.